Okay, so next let's look at D. D is another one that you can try on your own if you want, so pause the video if you want to try it. But I'll get started right away. So I noticed that there are two factors here. I have ln of x, and I also have division by the square root of x. If you want, you can write these all on one line just to start with, so that this looks a little more like an integral of u dv. So I could rewrite division by the square root of x as x to the negative 1/2 power. The negative would put the x in the denominator, and then the 1/2 power is telling us to take a square root. So these are the same. And now looking at this, I see that there's an algebraic component and a logarithmic component. So if we use the rule of thumb that we had at the very beginning, that would suggest that this should be my u, and that means that the rest of this must be dv. So now we'll make our little table. So u is equal to ln x. That would mean that du is equal to 1 over x dx. And here we have that dv is equal to x to the negative 1/2 dx. We would need to integrate that to get v. Now if I integrate that, I would add 1 to that power. So if you add 1 to a negative 1/2, it would be a positive 1/2. So we add 1 to the power to get a positive 1/2, and then we would need to divide by the new power. So that's division by 1/2. Now when you divide by a fraction, that's the same thing as multiplying by a reciprocal. So this is the same thing as x to the 1/2 times a 2 over 1, which is just 2 times the square root of x. Or if you wanted to keep writing it with this fractional exponent, that would be 2 times x to the 1/2. So now we have uv, du, and dv, and that means that we can use our integration by parts formula. We know that the integral of u dv is equal to, u times v minus the integral of v du. So I can just plug all of these in. So u times v is ln x times 2 root x. So that's u times v minus the integral of v du. And I think this time I'm going to write v with the fractional exponent just because we're about to multiply it by a power of x. So I'll put v du, and du is 1 over x dx. So this would be ln x times 2 root x minus, if you want, you can factor out that 2 from the integral because it's just a constant factor. But here we have x to the 1/2 divided by x. So whenever you have x to the 1/2 divided by x, you would be taking this top exponent and subtracting the bottom exponent, which is 1, if you want to think of it that way. So maybe let me give you another example just so that that's clear. If I was computing something like x cubed divided by x squared, then if I wanted to write this as just a single power of x, I can take the top exponent and subtract the bottom one. So this would just be a single x. The same thing works even when you have fractional exponents like this. So if you have an x to the 1/2 over an x, that would end up giving you a final exponent of 1/2 minus 1, which would be a negative 1/2. So this is ln x times 2 root x minus 2 times, and from what I just said, this inside would simplify to x to the negative 1/2 dx. And we've already integrated x to the negative 1/2 dx. We know that the integral of this ended up being v. So that was a 2 root x. So this last integral is just going to become a 2 root x. So this will be an ln x times 2 root x minus 2 times another 2 root x. And then because we just computed an antiderivative, we'll add c. And you could, of course, clean this up a little bit. Like this is just a 2 times 2, so clearly you could write a 4 root x, but you don't have to clean these up. I'm okay with you just writing it like this as long as you finish the integral and you write your answer in terms of the original integration variable. So that's the answer to part D. Lastly, we'll look at example E here. Now, this is a definite integral. So here we have integral bounds. So it is important to know what happens with integral bounds here. So this time we have ln of x to the fourth. I'm interpreting that like this, so that x to the fourth is what's on the inside of the ln. Now we don't know how to integrate ln of something without using integration by parts, but integration by parts will help. So we will be able to integrate this. So let's first worry about integrating, and then I'll tell you what to do about these integral bounds in a second. So let's first focus on integrating ln of x to the fourth dx. You can still choose a u and a dv even if you only see one integrand or one factor as your integrand, because I can think of this as being something like an ln of x to the fourth times a 1 dx if I really wanted to write two separate factors here. So these are the same thing, obviously, I'm just multiplying by 1. But the benefit of writing it this way is that now it's clear that we could select this to be our u, and if we did, then the rest of this would just be dv. And you can do that in the original if you'd like, so you can call this u and you can call this dv if you want. But I just wanted to make it clear that it's okay to select a u and a dv even if you only see one thing as your integrand. It's just that dv would just be this differential here, or in other words, 1 dx. So that's going to be my choice of u and dv. I chose that to be my u rather than dv because we have a logarithm here, and that's probably going to become nicer whenever we take a derivative. So now I'll make my little table. So I know that u is equal to ln of x to the fourth. And that means that du is equal to, you put the x to the fourth in the denominator, and then its derivative goes into the numerator. So this would be a 4x cubed over x to the fourth. And if you used the subtraction rule that I talked about a second ago, you could write this as 4 times x to the negative first. Or if you just wanted to cancel the exponents in the other way, then you could write this as a 4 over x. Either way, we end up getting this times a dx. So I'll write it as 4 over x. In either case, you should recognize that there's one additional factor of x in the in the denominator relative to the numerator. So after cancellation, we'll get a 4 over x dx. And we also know that dv is equal to dx, and that means that v would be the integral of dx, or in other words, the integral of 1. And the integral of 1 is just going to be x. So now we've found u, du, v, and dv. So we can use our integration by parts formula. Our integration by parts formula says this is uv minus the integral of v du. And that will be u times v, so ln of x to the fourth times v, which is x, minus the integral of v du. So this would be v du, like that. So this is v and this is du. And now we can clean this up a little bit and then integrate. So this would be ln x to the fourth times x, minus, here I can cancel these x factors because one of them belongs to the numerator and the other belongs to the denominator. So this would just be the integral of 4 dx. And when we integrate that, we would get ln x to the fourth times x minus the integral of 4 is just 4x. And if you'd like, you can put a plus c here, but because this is a definite integral, we won't really be using this plus c. So that's what we get as our integral. Now, we are not quite done because remember what we wanted was we wanted this integral from 1 to e. So we do have integral bounds here. So once you find the antiderivative, which is what we found here, now we can worry about the evaluation step. So what we get is the integral from 1 to e of ln x to the fourth dx is going to be this entire antiderivative, including the uv part. So it'll be everything, equals everything that we just wrote as our antiderivative. You don't have to include the c though, because those would cancel in the evaluation step. So this is our antiderivative that we just found, and then we evaluate this from 1 to e. So for this evaluation step, what we're going to do is we'll plug in the top bound into this entire antiderivative. So that would be ln of e to the fourth times e minus 4e. That's what I get if I just plug in e's everywhere for x, minus the evaluation at the other endpoint, so minus what we get when we plug in 1. So that would be ln of 1 to the fourth times 1 minus 4 times 1. And this does actually clean up quite a bit if you want. So this would be 4e minus 4e, because ln of e to the fourth would be cancellative. Those are inverse functions, so you would just get 4 for that first factor. So this cleans up to a 4 times e minus a 4 times e, minus, this is ln of 1, because 1 to the fourth is 1, and ln of 1 is 0. So that would be a 0 times a 1, which is just 0, minus a 4. Now do be a little bit careful. This minus sign in the middle, whenever you're doing your evaluation step, applies to everything that follows. So this minus sign applies not only to this 0, but also to the minus 4 here. In other words, you need to distribute this minus sign to the entire evaluation at the lower bound. But here we have a 4e minus 4e, so those cancel. We have a minus 0 and also a minus negative 4, so that would be a positive 4 altogether. So the answer here is actually just 4. Now, there is one comment that I want to make before I conclude here, which is that if you remember some of your logarithm rules, then you could have cleaned this up a little bit at the very beginning, but I didn't want to depend on those logarithm rules if you weren't familiar with them already. But if you remember them, you would know that you can pull out that factor, or I should say the exponent of 4, as a factor in front of the logarithm. So, in other words, ln of x to the fourth can be rewritten as a 4 times ln x. So this could be rewritten as the integral from 1 to e of 4 ln x. And then you could factor out that 4 from the integral if you wanted to. So that could simplify things a little bit at the very beginning, so that you just have a factor of 4 sitting around outside, and then you're worried about computing this definite integral instead. However, when you compute this definite integral, you would still want to be using an integration by parts trick, because we don't know how to compute the integral of ln x right away. Instead, we would want this to be u, and this would be dv, and then we would still proceed by integration by parts. So that's an alternative approach. I think I'm actually going to erase that whenever I post these notes, so I'm not going to include this because it sort of conflicts with the strategy that we used below, but I just wanted to point out that there is an alternative way of approaching this problem if you use your logarithm rules right at the beginning. So that's it for integration by parts. Our next lecture is going to be about just collecting some applications of integrals. So this is the last integral technique that we're going to talk about in the class. The rest of this is just going to be talking about some formulas that are used in